Hello everyone. In this video, I'll be explaining about how electromagnetic waves propagate in waveguides, which focus on their physical structure, modes of propagation, cut-off frequency, power flow, and practical engineering applications. Waveguides are especially important at microwave frequencies, where conventional transmission lines like wires or coaxial cables become inefficient. A waveguide is a hollow metallic structure that is designed to guide electromagnetic waves, typically at microwave frequencies. Well, unlike coaxial cable, it supports TEM waves using two conductors, which is a rectangular waveguide that uses a single conducting enclosure. The electromagnetic energy is guided by reflections from the metallic walls rather than by current flowing along a center conductor. So, TEM waves require both electric and magnetic field to be entirely transverse to the direction of propagation, meaning that there are no longitudinal field components. So, from Maxwell equations, this requires a voltage difference between two conductors. However, a hollow waveguide has only one conductor, and the entire wall is at the same potential. Because there is no potential difference, no transverse electric field can be sustained, and therefore TEM waves cannot propagate in a hollow waveguide. So, in a waveguide, mode refers to a specific field pattern that satisfies Maxwell's equation and the boundary conditions that is imposed by the conducting walls. So these modes arise due to constructive interference or reflective waves inside the waveguides. They are labeled as TE or TM modes, where the indices M and N indicate the number of half-wavelength variations across the width and height of the waveguide. So the dominant mode in a rectangular waveguide is the TE10 mode. This mode has one half-wavelength variation across the wider dimension and no variation across the shorter dimension. So it is called the dominant mode because it has the lowest cut-off frequency, meaning that it is the first mode that can propagate as frequency increases. So for TE10 mode, the electric field varies sinusoidally across the width of the waveguide and is zero at the conducting walls due to boundary conditions. So the magnetic field forms closed loops around the electric field lines. So this field configuration allows the efficient energy propagation while satisfying all electromagnetic boundary conditions. So for cut-off frequency, the cut-off frequency is the minimum frequency required for a waveguide mode to propagate. So for the TE10 mode, the cut-off frequency is given by Fc is equals to C divided by 2A, where A is the wider dimension of the waveguide, and below this frequency, the wave the, from this equation, we can say that below the frequency, the wave cannot physically fit into the transverse dimensions of the waveguide. When the operating frequency is below the cutoff frequency, the propagation constant becomes imaginary. Instead of propagating, the field decays exponentially along the waveguide. This phenomenon is known as evanescent decay, where energy is stored locally rather than transmitted forward. In waveguides, phase velocity and droop velocity are completely different, where phase velocity describes how fast the wave pattern moves and exceeds the speed of light, without violating the relativity. And group velocity represents the speed at which energy and information travel and is always less than the speed of light. So waveguides are dispersive structures. That means velocity depends on frequency. As frequency approaches the cutoff frequency, the group velocity approaches zero, while phase velocity increases. So these two velocities are related by the equation Vp times by Vg equals to c squared. So from the power flow, the electromagnetic power flow is in a waveguide is described by Poynting vector, which is the cross product of the electric and magnetic fields. So this vector points in the direction of energy. So this vector points in the direction of energy propagation, which is along the axis of the waveguide. And for the wave impedance of a TE mode depends on frequency. Near cut-off frequency, the impedance becomes very large, causing strong reflections. And at high frequencies, the impedance approaches the free space value around 377 ohms, and the waveguide behaves more like open space. So the waveguides are preferred at microwave frequencies because they are offer very low loss and can handle extremely high power levels. Since the dielectric is air and there is no semiconductor, dielectric heating and breakdown are minimized. So for the constraints and applications, waveguides are widely used as radar systems, satellite communication, and 5G infrastructure. However, they are physically large at low frequencies and operate only within a limited frequency band to avoid higher order mode distortion. So in summary, waveguides guide the electromagnetic energy using metallic boundaries rather than conductors. So only TE and TM modes can exist, with TE10 being the dominant mode, cut-off frequency at as a high-pass filter, and waveguides offer efficient high power transmission for microwave engineering. So I think that is all from me. Thank you.